Volcanoes. What are they? Why we have volcanoes? And where on Earth they exist? In this video, we'll talk about volcanoes. What is the nature of the volcanoes, why we'll have them on our Earth, how they behave, and what it depends on. And we'll consider it in the light of where they are occurring on our planet. The type of eruption that happens depends on the magma properties, the type of topography they create, and how it's related to plate tectonics and the geology. What comes to our mind when we talk about volcanoes? Classically, we're thinking about the single mount of cone shape with a smoky top. However, it appears that on our planet there are much more varieties of volcanoes, and let's look closely what it depends on. First, let's understand what is the volcano. As we know, on our planet we have a hot material inside of our Earth. In the very center of our Earth there's a furnace. The metal core exists, which generates a lot of heat, which causing the distribution of heat through the main body of the planet to the surface, and to which we're thankful for different varieties of minerals on our surface, which give us life. Important gases to form our atmosphere, water to give us life and feed everything on our planet, plant and animal life, and also the different minerals from which the crust of the atmosphere is composed of, and everything feeds on our planet. So the volcano is essentially this place with this warmer material coming out on the surface. The heat is coming from the outer core, and it's a very high temperatures there. You can watch my previous video about inner planet properties and about formation of our planet Earth. You will learn that in the outer core of our planet we have temperatures as high as on the surface of the sun. Therefore, all this heat should go somewhere. You know, when you boil in a jug, the heat coming out in form of steam. The warmer material starts mixing in the mantle, which is semi-molten material of different properties. And the closer you come into the surface, the more complex minerals they are, and the more you're going towards the center of the Earth, the heavier are minerals there, and the majority of them are metal ones. So as a result of this heat redistribution, the planet trying to cool down. The planet tried to cool down since it was formed. After the formation of the furnace, the core of our planet, we trying to cool down all the time. So the heat started warming up this semi-molten material, which we call the mantle. As a result, some material warming up, getting lighter and rising up. When it's reached the surface, it cools down, and in comparison with the surrounding cooler, it feels heavier and it starts sinking back down. And that's how we created this circle of the material, creating like cells all around our mantle. We call it convection cells, and it's exactly which drives the magma or this molten material to come up to the surface. And the place where there's some particular openings in our crust, usually it's where there's some kind of meeting of the plates, or just in the places in the middle of the particular continental or oceanic plate, and the magma finds its way out through the cracks or the vents like a volcano. And the different types of volcano created in that places. So the material which are still within the Earth's crust, so it didn't come out on the surface, we call magma. And it's usually material which made up of the semi-molten rock. It's type of liquid which made up of dissolved gases, volatiles we call them, gas bubbles, and the crystals. Crystals, it's material that had time to crystallize in particular temperature. So not all the crystals crystallize in one temperature, surface of the Earth. Some can crystallize under the high temperatures, and they first crystallize while they're still in a hot mantle. or somewhere on the way up. Dissolved gases, it's all the gases that absorbed by this melt of the magma, we call it volatiles, and in particular condition when we change the pressure or increase the pressure, they separate from this melt and become as a gas bubbles. And the more water you have, and the more you're moving through the particular medium, these gas bubbles start reacting like bubbles in a bottle of champagne, and it's usually the reason why we have such explosive eruptions of volcanoes sometimes. So that's what the magma is consist of mostly, and when it's come out on the surface we call it lava. So it's the same material, but the moment it's come out of the crust it's become lava. Lava could be in this semi-molten form and it's fluid, or sometimes it could be pyroclastic material. We'll call ashes as well. So pyroclastic materials or the ashes, it's already in form of the minerals that the magma coming out to the surface because it cools down very quickly. So that's the main idea, what's happening with the material that coming from the center of the earth. And this happens everywhere, all around the planet. We will look in particular geography where the volcanoes occurring and why. We need to understand that the magma behaving not like a water, so it's more behaving like a viscous type of material because it's composed of different crystals, gases, and often the water. It is a viscous, it's very sticky, and you can compare it to the toothpaste. It will flow if you have particular angle or enough viscosity, but then it will stop flowing. So it won't be like a water spreading a thin layer over the surface. It will behave more like a toothpaste. And it also will vary from volcano to volcano. It depends on the composition of this magma which coming out in this particular place. Understand the volcanoes in different varieties of them, main types. We should consider the properties of the magma. Usually people categorize 3 main types of magma. You can categorize a little bit more, and it will depend on from how deep from the ground they're coming, what medium they're coming through before they're erupted, and that will determine the types of eruption. As we talked, viscosity of this material. It depends on the gas content, silica content, and it will determine how explosive this eruption, and usually those eruptions will be characteristical for particular places. For example, if we look for more basaltic type of magma, this is the one that comes more from the upper mantle. This magma is very heavy, it's very rich with the metals in it magma, such as magnesium and iron. It have very low viscosity, so it will be more fluid, so it will be flowed a little bit faster, so it will be more active when it's spreading, and it will have lower gas content. We know that the silica content will be about 50 or less % in the composition, and we usually find this type of lava in oceanic and continental crust. You will not observe big explosions there because not enough gases, not enough silica content, and there will be a more slow and calmer type of eruption. Usually this is the smoky volcanoes that sit in the bottom of the ocean under the water, and they have this pillow lava formation. And it's also those volcanoes, for example, like in Iceland, that coming out from the big cracks rather than the cone-shaped volcanoes. Different, they're not a violent eruption with a lot of ashes and smoke. There will be more just a lava flowing out of the cracks. There will be an intermediate type of the magma, which is sourced from oceanic crust and oceanic sediment. A little bit more gas content, and usually oceanic crust and ocean sediment had much more water composition as well. The silica content will be a little bit higher, but not as high as the 4 continents. Explosiveness will be intermediate, and we usually find those volcanoes on continental margins and around the subduction zone, so we'll look closely to those two. And the last type is rhyolitic type of magma associated with continental crust, and you can imagine it will have higher gas content and more silica content, because there's a lot of silica in the continental crust, and in basaltic oceanic crust a very low content of silica and mostly metals. See my video about plate tectonics to learn about that. And because of that, there will be more building up of material, and these gases will be like a bottle of champagne bubble up more and pushing through this continental crust material, which will cause more explosive type of eruption. And the composition a little bit different. There's more silica, so there's a bit more material which will be crystallized differently than the basaltic one. And we have the more pyroclastic type of flow, explosions, a lot of ash, and it's usually those volcanoes you can find around continental crust. Viscosity will be quite high, so it's mean the material not gonna move as fast and as far. You might find that you're a little bit confused right now about these magmas and volcanoes, but the more we look through later, through the volcanoes and where they're located, that you will understand it more. From this table, I just wanted to take it that the chemistry of the material, magma which composed of, very much determine the physical properties of the magma, how it's behave, and which temperatures it's crystallized. And we know that the more silicic or felsic type of material, so more silica you have in the material, more continental type of magma you have, the higher the viscosity of this material, and the more ultramafic or mafic type of material, basaltic, in other words, the less viscosity you will have. If you're confused still about the viscosity it's how fluid something is, how behave as a fluid something. So the water have a very low viscosity, it's less sticky. And for example, then the honey will have a little bit higher viscosity, so it's more sticky. And the things like toothpaste, for example, have even higher viscosity than the honey. So they're not going to spread as far around your table, it will stay in the form of tube. Similar with the magmas and the composition. So if you look in this table, you're going to go from basaltic, less stickier type of material to the rhyolitic, more stickier with a high viscosity. Therefore, bear in mind that the chemistry, the crystals of the material, the magma, will determine types of explosion you're going to have and types of volcano you will end up with. If you look on this diagram, you can see very schematically the very typical volcano and the way how it's connected to the mantle. We have granitic batholith, that's the place where the high mantle is, it's deeper into the ground. And the deeper to the ground you go, the slow cooling happening, so the crystals are growing bigger, larger. You can imagine if you have a lot of time to grow crystal, they're gonna have more complex structure and they'll be bigger. So those nice crystals you find sometime shines in some granites, for example, it's mean they come from the deeper ground, so they form when they're underground. And the closer towards the surface of the earth you're moving, the faster it takes for magma to cool, because we have much bigger difference in the temperatures. For example, when the magma come out to the surface, it's interact with the air, which is much cooler. The surfaces, like the rocks on the surface or any other surface, it will cool faster. And as a result, it will be not enough time to grow crystals, and you will end up with type of lava such as pumice or ash, very fine grain volcanic rocks. It's very good for geologists. When you find your rocks, you know they are volcanic, you can identify where they were crystallized, closer to the surface, on the surface, or deep under the ground. So you can see that when you grow the crystals in the batholith, they are bigger, and then the material moves up through types of dikes towards the surface. Dikes, it's the passages that go through different layers of previously deposited rocks, which the hot magma go through. And it's very easy to determine them when we look through the cross-sections in the field. We can identify direction of the flow, how it's been cooled, especially if those dikes cutting through different previously deposited layers. Obviously, the material in these dikes will be younger. These dikes are quite complex. They're trying to find the passages through the cracks, pre-existing cracks in the earth. And the volcano have many types of dikes, sometimes forming some side, smaller eruption, but eventually it will go through the main vent and erupt in a big eruption to bring more material to the surface. For example, famous Taranaki volcano, classical cone-shaped volcano, have two tops, one bigger one, which erupted more often, and the other smaller one. So sometimes eruption happening through the smaller dike side volcano, sometimes through the main one. You can also see sometimes dikes go between the layers, geological layers, and we call them as seals. They essentially absolutely same, have same properties as the dikes, only they go horizontally. This is just the way the magma finds its way out through the surface of the earth. So what are the volcanoes? Volcanoes, it's the vents in Earth's surface through which magma and volatiles erupt. Called volcanic activities all phenomena of discharge of magmatic material from the down underground of the earth to the surface. Therefore, we have a variety of the volcanoes. So typically we can differentiate main type of eruptions. First are the, as we already say, fissure eruption, kind of eruption coming from the crack, and it's usually not as we imagine cone volcano type of eruption with a lot of smoke. It's actually eruption looking like the wall of the fire, and especially it's better observed at night. There's more basaltic type of lava usually involved, and we have less gases and volatiles there. We can call this type of eruption more liquid eruption, and it looks like fontaining type of lava out of the big crack. Usually this type of eruption we observe or in the places like Iceland, where we have the rifting zone, more basaltic type of material coming out, we'll talk about later, or when we have, like in Hawaii, the hotspot type of volcano. Next type of eruption, it will be the solid crystals eruption with proper clastics usually, and this type of volcano very explosive, and they actually are erupting a lot of solid material when it's happening, and the big cloud of ash spreading all around. And we also have different types of volcano with just slowly releasing a lot of gas. We call them the gazing fumaroles, and the places like White Island in New Zealand, it's a very famous place. Sometimes there's happened some eruption with pyroclast, but more often it's just the gases smoking slowly out. Different types of volcanoes depends on the situation where they're located relatively to the plate tectonics. You can have the positive and negative type of volcanoes as well. For example, you see these causing a building up of material, the cones traditionally, or just some bulging of the material. We can have dome type of volcanoes as well, which building up material on the surface and eruption happen from time to time. However, sometimes we have very big eruptions. Big eruptions, they building up for a long time and then they explosively coming out. And I'm not talking about those when we just have part of the cone of the volcano erupted or landsliding during the eruption. Like for example in this Mount Helens in 1980, when there's an eruption build up caused the bulge of the material on the side of the volcano, and then eventually it's erupted and the big landslide collapsed a third of the volcano down. We're talking about a catastrophic eruption when there's so much material built up for a long time and as a result it's blow up. Usually it's related to the supervolcanoes. We call them super. It's a huge, extra, super big eruption. And one of the famous you know about is the Yellowstone volcano located in the United States. However, this volcano haven't been erupting for a very long time. From more recent ones we know about, it's the New Zealand Taupo volcano. It's a supervolcano and it's the biggest eruption that happened in the last 75,000 years on our planet. When the Taupo eruption happened, there was two recent big ones. So much the Earth's crust erupted out that caused a volcanic winter all around the planet and affected everything around. The ashes spread all around through half of the North Island and into the Pacific far away. The solid crust was removed, and in this depression, we call it negative type of topography created from this eruption, we have the water fill in and creating the biggest lake in New Zealand right now, Taupo. So next time when you look at a map or traveling through the Taupo, understand that the Taupo Lake is the crater of the big supervolcano. So where are volcanoes located on the Earth and why? As we already mentioned, you should look on the formation of the Earth and the plate tectonics of the Earth. That'll be your clue where you should look for volcanoes. If you look on this map, we can see that here, highlighted with the red, are the main volcano chains. And for example, around Pacific, we have the so-called Ring of Fire, the location of all the volcanoes that coming from through New Zealand, Pacific Islands, Indonesia, Japan, east of Russia, Alaska, the coast of United States, through the Central America down through the Pacific. All around the Chiles, all around the west coast of the South America, Andes, and we call this Ring of Fire for that. This is a very active place. There's a lot of subduction happen when the oceanic plates come in under the continental plates, or the two oceanic plates meet each other, and that's where the volcanoes are forming. Watch my bigger video about plate tectonics when we talk about the reasons why we have this specific geography and how the plates behave. However, here we mentioned just briefly about that. But you also see that volcanoes located sometimes in the middle of the tectonic plates, or there's a chains of volcanoes in the places like Eastern Africa, coming from the Red Sea, in the middle of the oceans, associated with mid-oceanic ridges. So those volcanoes are located in the rifting zones. That's the place where the plates are actually created. So that's the place with happening spreading of the crust. If you think about these conventional cells, that's the place where there are a lot of magma rising up constantly. And the crust, if it's oceanic or continental, it's spreading apart. And as a result, thinning of this crust in that place, causing like this baking up from the mantle and the material rising up and through the cracks, especially Mid-oceanic regions, there's a lot of cracks, the eruptions happening. In the bottom of the ocean, most of the time, the lava just floating out through these cracks into the water. It cools down very fast under the pressure and the temperature of the water in the ocean. And we have this creation of the pillow lavas. You can see how they formed. They look like a toothpaste being exhumed into the water. You can see that the water all surrounded the lava flow, causing its fast cooling. And it's very interesting, looking like a worm coming through the soil. The lava flows down on the bottom of the ocean. It's very characteristical, and geologists can identify those in the deposits later. But not all the oceanic crust volcanoes located under the water, some of them coming out on the surface. And if you look on Iceland, what is the Iceland? Essentially, Iceland is the land that been built and created from constant eruptions, and there's so much material built up there. It's become so big and high, and it's caused the formation of this big land on a rifting zone. You can imagine, and that place, there must be that the speed of the magma that coming towards the surface higher than the speed of spreading. So we're moving apart the material slower than we're accumulating material, and as a result, you will know, you will end up with a pile of material on top of each other. That's exactly what's happening. There's a very high rate of explosion bringing material, magma, to the surface. In the middle of the Iceland, we have this big kind of crack happening. That's where the ground actually sunk in through, and in through these cracks, a lot of eruption going on. Actually, this video showing the eruption, fissure type of eruption, like a wall type of a very basaltic type of magma on the surface. There are not many places like the Iceland around on the Earth, so it's a very unique place to visit and watch those volcanoes themselves. And other places with the rifting, as we say, it's for example east of Africa. And you can see here the Red Sea. It's a very narrow sea, supposedly, and there's a volcanoes located along that and continues down south, and that's where the main African volcanoes we have. And one of the biggest, the rifting zone volcano, Kilimanjaro, on our planet Earth, located. And you see that this crack in the middle coming through the whole Africa continent, divided it into this eastern part that moving southeast, and the other rest of the Africa continent moving to the west. So all this place, including the Red Sea, down through the Africa continent, through the Lake Victoria, where the volcanoes are located, it's the place when the new ocean is started its life. Similar as many million years ago, the South America and Africa used to be one continent, and the rifting zone like that occur, like right now we observe ourselves in Eastern Africa, the continents start spreading, and now they're so far apart, but we can still match the coasts of these continents. Similar here, the Indian plate moving away from the African plate and the new ocean created. And of course, it's all associated with volcanoes here. A very interesting place to look at all the geology of Red Sea and down towards south of the Africa. If you look on schematically on this type of place formation of rifting zone, usually they might be located behind the subduction zone. Two plates are actively moving toward each other, and as a result, behind you have this thinning, spreading apart plate crust. And that place, the magma is through the series of dikes rising up towards the surface, and as a result, also this thinner part of the crust can sink down, and in geology we call it the grabens formation. A lot of cracks happening there, and that's where the magma as well will find its way towards the surface. You can see here in Eastern Africa example of this type of graben. Usually these volcanoes is one of the biggest ones we can find classical on our Earth. So next type of volcanoes could be the volcanic arc created in these subduction zones. So you will have the one plate going under the other, and in this case we have the oceanic crust coming down because it's heavier and denser under the lighter continental crust. But all this sediment material that will be dragged underneath will be very saturated in the water, high water content, and because of the increasing temperature and the friction there, the pressure, we have a lot of dewatering happening of this material, and it will cause a lot of gases formation. You can see it's rising up through the magma chamber and causing the new magma rising higher, creating the formation of the series of volcanoes. Usually those volcanoes find in a line following these subduction zones, and the very classical one is already said around the Ring of Fire. For example, in the Andes you have the series of the volcanoes going all the way through the western coast, very typical numerous volcanoes just behind the subduction zone. As you can imagine, this will have intermediate type of material with a mixture of oceanic crust and oceanic sediment. So usually you can find those volcanoes around them. This is what you can find on the subduction in the continents, and in the places where two oceanic crusts collide, you can find the chain of volcanoes in the ocean, volcanic islands created in the arc. In the Western Pacific, we know all Indonesian islands, it's created like that, Japanese islands, the famous big volcanoes and that areas. In New Zealand, we have the Tonga Kermadec Island Arc, which is the place where the Pacific and Australian plates meet under the ocean. We have series of the volcanoes associated with that. And sometimes we have a situation when we have the mantle plume just occurring somewhere around the mantle, under the ocean crust in the middle or under the continental crust. It doesn't have to be associated with the collision of the plates or rifting of the plates. And this can happen anywhere, and with a very famous place we know in the middle of the Pacific plate, it will be the Hawaiian Islands. They're located over this mantle plume. It's quite buoyant and it's rising up through the mantle towards the surface, creating the series of volcanoes. And we have the plate tectonics there, so the plate keep moving, and the next time the plume reaches up the surface, the new volcano eruption happening, new islands created. And those ones that move away from it with time, they slowly dying out. So this is the classical for oceanic crust, for example, the movements of the Hawaiian. You can trace through the Hawaiian Islands, the ones that are very active, constantly erupting today, the islands, towards the ones that already die out, and they slowly eroding away. And because it's located in the ocean, we have the corals occupying those islands quite often, and some other sorts of erosion happening. Sometimes those islands just disappearing at the end. These hotspots can also happen under the continental crust, and in fact the very famous one will be the mentioned Yellowstone supervolcano. It's just under the middle of the continental crust, big plume of mantle coming up towards the surface. And if we look through the history of Yellowstone, it's actually moving along the plate as well. So the plate's moving away, but the plume staying in the same place, and as a result, the volcanoes constantly shifting. These hotspots are amazing, and one of the best places to go and see the actual eruption of the volcanoes will be Hawaii. So in summary, you can see that the types of volcano, the way where the magma coming out on the surface are so different, and there's so different types of eruptions happening and different hazards associated with them. And if you live in the area next to the volcano, you should know the strategy what to do in case there will be eruption, how active your volcano, and follow the instructions of the specialist how to save yourself in case of emergency. However, usually when eruption happen, apart from big landslides, pyroclastic, big landslides that can be associated with it, usually they're not as dramatic or catastrophic, and the lava is very viscous. Most of the time you can actually outrun it, and often geologists go to the volcanoes and they can walk next to the lava, watch its flows, observe it, maybe study, take samples. Some of the volcanologists like to warm up the tea on top of the lava and so on. However, you always need to follow the specialist. There's also the tourist type of visiting of hot lavas. You can do that. So the volcanoes, it's not like very destructive and it's mean everybody gonna die all around them. So you need to be very wise about that. However, majority of us are afraid of big explosive eruptions on our planet, which can cause dramatic, catastrophic consequences. For example, those volcanoes in Iceland, when they erupted in 2010, famous, we had interruption of the flights to the Europe for some time because of the pollution in the air. And similar, when there was a Pacific Island eruptions, there was problems with the flights from New Zealand to the direction of the America. But we do not observe very often this type of events, the big events. For example, the biggest recent eruption happened in 1815 of Mount Tambora in Indonesia and create global climate anomalies. So there was a climate effect all around the planet, and we talked about this in a little Ice Age video. There was the year without the summer, from all these ashes and dust in the highest levels of atmosphere, which was circulating there throughout the year, and there was a very cold winter following that. However, the biggest event that happened 75,000 years ago, it was super eruption of Lake Toba in Sumatra Island of Indonesia, and it's almost caused the extinction of population of people on our planet. The scientists suggested it's affected the genetic inheritance of all humans today. This eruption was huge. There was a big supervolcano eruption, the one we're afraid might happen in Yellowstone. And people just suggesting that in the past, the events of major extinctions of the life on our planet, such as Permian-Triassic or late Devonian mass extinctions, watch my video about mass extinctions, they could be associated with big eruptions. I hope in this video you have some kind of understanding about the volcanoes, where they're located, why, and you got the understanding that they're quite different, depends on the material that erupted, geology of the place where they are, and it will also determine that they are there. Either it's a subduction zone, or the rifting zone, or it's the hotspot type of volcano. And I hope next time you will hear something about the volcano, you will think about the geology and what type of eruption you should expect there. We'll talk about some famous volcano eruption events or supervolcanoes in the future videos. I hope you'll stay with me, subscribe, and share this video with anyone who might be interested. Thank you for that.